So the talk of today is about mathematical considerations about fly's flight. And to be more precise, it's based on this paper, right? So 2022 Nature, building an allocentric traveling direction signal via vector computation. So we will discuss this paper, and of course you have to have a look at the paper itself directly, and there are also some videos available where ABOT explains more in detail what this is about. All right, so here I will take the point of view of the course, which is dynamical systems, networks, and applications. So it's the point of view of the network, how networks and math can model some biological phenomena. And in fact, this is quite a very interesting paper because it shows that the fly's brain do vector computations. So it's quite intriguing. Yeah, so this is really good for math because the math are at play in the brain. So the brain acts like a computer who does computations. Okay, so let's put these two things. We're just reading that. There's also this is not an article. These lines come from the so Abbott is professor at Columbia University, and the other ones are here at Rockefeller University, and so on their website, it's very well explained to grab the main ideas. You can have a look also at that. And what does it say is that this is known. The fly brain has a set of neurons that signal the direction in which the body is traveling regardless of the direction in which the head is pointing. So we'll come back to that, but basically you have kind of a compass, right, in the fly's brain. So you have some neurons, and you can observe a bump in some neurons, and this bump in the neurons is related with the direction where the head is pointing. However, sometimes your head is pointing in one direction, but you're going in another direction. And so that some neurons point in some direction was already known. What this paper does, it shows evidence that other neurons have a bump that indicates the angle for traveling. Okay. Yeah. So typically, for example, you're walking forward, so the fly is going forward, but then a strong wind comes and pushes the flies back. Then you have two directions. The head is still looking forward, but the bodies of the fly is pushed backwards, and so you have another neurons in the brain that indicates that. And how this is done? This is vector math. So here you can read in vector math is more than just an analogy for the computation taking place. Rather, the fly brain appears to be literally performing vector operations. We make a strong argument that what's happening here is an explicit implementation of vector math in a brain. So, and what they did, they make evidence, they show how the neuronal activity in the fly's brain is related to quite sophisticated mathematical operations. Yeah. Okay. All right. So let's move with that. Okay. So yeah, those are taken from the paper. So what's important here for the talk of today and for the work that is proposed, you have so what we're looking at is the central complex in the fly's brain, right? So this is in this part here. This is the classic Drosophila that is studied in biology labs. Okay, so here the central complex is represented here, and you can see some things here. This is called the ellipsoid body. Let's do it with that. This is here, this is ellipsoid body. So as you can see, it's a disk. And as far as I understand, that's quite impressive because you will see the behavior is related to angle. So the fact that this is a disk is very convenient because each region in this disk is associated with an angle with the direction. Okay, then you have here the fan-shaped body, okay, because it has the shape of a fan here. And here you have the protocerebral bridge, okay? So those are the main parts relevant for this study, okay? So within these structures, what you have EPG cells. And so you can see that EPG connects the ellipsoid body with the protocerebral bridge. So in fact, and you can see that in the videos made for Professor Abbott, there's a copy. The activity here is copied in the protocerebral bridge. So, and the EPG make the connection. So EPG are neurons. So actually E stands for ellipsoid, P for protocerebral, and G is for GAL, but we're not going to talk about this today. Okay. And so another important structure here, it's the H delta B cells, and they are acting in here in the fan-shaped body. So according to the video of Abbott, there's a lot of computations going on here. It's like yeah, some part of the computer is going on there, and yeah, so you can observe, you can measure H delta B activity, and you can measure EPG activity. So it's more easy to say than do it. This requires sophisticated tools to measure that, but some people did it. So we're just saying it, but so that requires a lot of work. Okay, here it's an EPG cell. Okay, and so there's a tool to do that, and I think Oh, yeah, but so there's a tool to do that. So new print, and it's very interesting because what? Because the connectome of the central complex, um, or a huge part of it, has been established, and they put it in a software, so you can go yourself and look at the neurons, how, what is their shape in 3D, uh, uh, what are their connections in the brain, and you can do it all by yourself. So actually, in this lecture, in this session, I propose you to go to this software and do it by yourself. All right, so let's move forward. So um, I connected to the new print here. Uh, the idea is to get kind of our hands in the fly's brain, and so this software allows that. So let's have a look. So we're looking here in this part of the brain. So if I click here, yeah, I can see here. So I come here, and this explains. There's a lot of information about the 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 fly central complex, the fly's brain. So for example, if I look at that, all right, so there is this video who explains uh, the general functioning of uh, so this is the ellipsoid bodies of visual ring neurons. And so you can have a look at all these things. That's very interesting. So you can see here the different parts. So uh, there's no sound, but you can have a look. Okay. Okay. So let's come back and try to illustrate. So you have the brain region connectivity. So here you have some neurons. How neurons connect together. Okay. And so, for example, let's see, we spoke about EPG and H delta B. So if I go from the ellipsoid body here toward the protocerebral bridge, all right, I submit here, and I can see the EPG neurons appearing here, and I can, for example, visualize one, and okay, it's here. All right. I can also look for example, H delta B. For example, this one, and all right, okay. So uh, everything is well documented. There's a software, so you can almost get your hands in the fly's brain. So again, that's very good for the modeling of networks with dynamical systems, because here what you have is access to the relevant network topology in the fly's brain. All right. Okay, so now let's come back more in detail for the fact that there's a heading angle which is different from the traveling angle. So as I said, so I already said that, but here I read it for more detail. So these sentences are directly taken from the article. I might change it a little bit, but it came from the paper. So the full population of EPG. So what do they do? They measure the calcium activity during flight. So they have techniques to simulate the flight of flies, and they measure calcium activity in the brain. And what they see, it's a bump of calcium activity in the ellipsoid body, and copies of this bump in the left and right bridge. So this is the ellipsoid body, left bridge, right bridge. And they track these three signals shift in concert along these structures, tracking the angular heading of the fly reference to external cues. Okay. So this is for what? This is for EPG. So the EPG moves in concert with the heading direction of the fly. Now, they also, and that's the point of the article, they also measured what was going on in the H delta B cells, and this revealed a bump of activity along the fan-shaped body. So fan-shaped body. This is correlated with the EPG. In fact, if your head and your body are going in the same direction, that's the same. But as we discussed, if there's wind, then the body and the head are not going in the same direction, and then you can see a difference. That's right in here. Okay, so what this article suggests is that the H delta B and the calcium bump observed there might signal the traveling rather than the hitting angle of the fly. Okay, so now, of course, your students of math, graduate students of math. So we need to have a look at the equations. So you can find these equations on the videos that are on the website. And so these are the equations for the bump activity in the EPG cells, in the ring of EPG cells. So let's have a look there. So it's a network. It's a network of ordinary differential equations. So you take the derivative of R. So hi, this is the calcium concentration. And so the model says that the derivative of the calcium concentration at the node I, so it decreases to 0 if it was not connected, but so you will excite this calcium activation with some connection. So here it's the connection with other cells in the brain, and here you have a drive. Okay, and then here you have some function. So here we'll make some numerical experience with f equals 0 if what's inside is negative, and its identity if what's inside is positive. Okay, so yeah, there's various possible f. This would require more discussion with biologists, what kind of f choosing. So it looks like you can choose f equals 0 if what's inside is negative, and f identity if what's inside is positive, right? Okay, and then the connectivity matrix looks like that. So theta I, theta j, those are constant. So theta I and theta j are angles in the ellipsoid body. Okay, so those are numbers. So let's say my node I so my node I, it's a fixed position in the ellipsoid body, in the ring. Okay, so for example, you'll have theta I equals 0, so theta 0 or theta 1 equals 0, then theta 2 equals, depending on the size of the networks, we will make some tries numerically. And so R1, it's a 0. Okay, I see the question. I will answer that. So let's say I goes from 1 to n, capital N. So I1, let's say it's angle 0. Now I equals 2 is angle 0 plus some a space step times 2 pi. All right, and you go all around your ellipsoid body, and you have, so each I, it's a fixed space on a disk, on a circle actually. Okay, the I is a fixed position in a circle. Okay, so it goes basically from 0 to 2 pi. Okay, we could have a continuous model. This is a network. All right. Then what? And so next you have how each I is connected to the other locations. So this is connection between neurons. So how the neuron I connects to the other neuron. So basically here it receives excitatory or inhibitory signals, and those are numbers. So theta I, and so this is fixed. This is fixed between the node I and the node J. This is fixed. All right. So you have various parameters, J node, J high here, theta I and theta J are locations on the circle. Then you have a parameter L, and so you see here you move in a direction. So if you move from pi divided by 4, you move to the left, so, and it's associated with the coefficient L. And on the other direction with R, which is right. And here you have some drive. So of course, this is, again, this is just an introduction. There's a people working on that. I just took that from the article and the things that are available to the public. So VI stands for the light that the brain of the fly receives. This stands for the long range interactions, and this stands for the local connections. Okay, so what I propose to do now is to try to have a more in-depth look at those equation and in fact try to simulate a little bit those equations. Okay, and just before to do that, this is an illustration of the bump activity here. You see the bump activity here on the ellipsoid body. And so you can see this indicates a direction, right? So this, you see a bump, and this is correlated to the heading direction of the fly. And you have a copy. So this is for the ellipsoid body. And you have a copy of this signal in the protocerebral bridge. Okay, so as an exercise, try to look at the equation. We want to understand a little bit better what's going on. So as an exercise, try to do this simulation with L equals R equals I equals G node equals 0 and GI equals 1. Yeah, tau you can choose 1. All right, so let's try to let's play with this equation. So we will use the, well, it's classical. This we use Python, so I use the simplest thing. So we'll solve it as an ODE. We'll use the software. This is a function from Python. What's important is that we need to define our matrix of connectivity. So let's look at that. For example, let's say I choose n equals 6. So if I choose n equals 6, I divide my ellipsoid body into 6. So 0 p divided by pi divided by 3, 2 pi divided by 3, pi, etc., etc. Okay, and then I construct this matrix. So this is just to construct a matrix, and to show you that, I just copy here those lines and I put them here. Okay, and so this line of codes are just to obtain a connectivity matrix. So, and this is made of the cosine of theta I minus theta j. So for example, here I'm at 0, so my theta is 0, and so it's theta 0 minus theta 0, which is 0, and cosine of 0 is 1. Next I do cosine of 0 minus 2 pi divided by 6, which is pi divided by 3. And you all know that cosine of pi divided by 3 is 0.5. Okay. Next, I have cosine of 2 pi divided by 3, which is minus 0.5. Then cosine of pi, which is minus 1, and so on and so forth, until I have all the points in the circle. Okay. And then I do the same, but then the second line, so second line corresponds to theta 1, which is pi divided by 3. When I do pi divided by 3 minus 0, I take the cosine, and I got 0.5, then I got 1, etc., etc. So the successive lines of my matrix, I just shift the lines, and until I have the 6th line. So the matrix is symmetric, and each line is a shift of the previous one. Okay. All right. So this is for n equals 6. Now I can take a larger n, for example, 20. And then I will solve my ODE. So what I need to implement here is my function f. So my function f is here. Here I just apply a times u, but I'm going to take the maximum between a times u and 0, which corresponds to my function f. And then here I have my ODE. So let's start with if everybody is constant, if my initial condition is constant, so let's say I start at everybody is equal to 0.5, I run my program, and everybody has the same shape, which is actually 0.5 exponential minus t. Okay, so in this case, well, you can check that. Let's redo that. Oops. So let's oh. So when you have a matrix like that, in fact, if you sum up all the lines, it's 0, which means what? Which means the vector made of ones is an eigenvector of this matrix associated with the eigenvalue 0. Okay, so if I start with an initial condition which is constant, then the f term disappears. Right? If in this case, and so if the f term disappears, you just have the equation u or ri prime equals minus ri, and the solution is exponential of minus t. And because I took as initial condition half here, you have the exact solution. Okay. All right. So now let's have a look at other initial conditions. And for example, if I start here with an initial condition that goes from 0 to 1 with n values, let's see what we have. All right. Now, next I have that. So I have different values. Okay, so all right. So here we have some, at some point, everybody is going to 0, but I see that 15 here is not going to 0. So we will need to explore that more in detail. From a biological point of view, of course, you have parameters to adjust, and this should be studied mathematically. But for the biologists, use this equation, this part of the equation, to get the bump. But let's say that this is, at the end, this is a stationary solution with a bump. So it looks like we have it here, but this will require more investigation to do. For example, let's say what we have at 14. And what we have at 18. All right. So it looks like we have a bump when you see. So of course, this is just an example, an invitation to work on that. But it looks like you have a bump. So I have 20, right? 20 here. So let's say 19th. It's the last. All right. All right. So now I can also look, which is natural, at the profile at the end of my time for all spaces in my network. And so here, so I solve. You can see here I solved my ODE until t equals 20. So I'm looking at the n. So if I look at t equals 19, and I look at the value of my concentration, calcium concentration at each time, I will get this bump. All right. Now, what the biologists are able to do, neuroscientists are able to do, is by adding those other terms, they can move this bump, and this is correlated with. So this follows the bump of calcium activity in the ellipsoid body during flight, and this is correlated with the head direction. All right, so we've gone through some simulations. Of course, if you want to get closer to the reality, you have to adjust all these parameters, make them dependent on time. So at the end of the day, it will not be an autonomous equation. And it's interesting to look at all these details from the neuroscience part, of course, but also from the mathematical part. Okay, so to end the thing, uh, that's quite an amazing job that they did. All of these contributors to this field. And so to end this lecture, just a few words. So I said there's a difference between the heating direction and the traveling direction. So according to their findings, to their articles, what they say, and they made a lot of measurement to that, is that so first you can observe directly that the ellipsoid body tracks the heating direction. Now, what they did in this paper is that showed that they have also the H delta B cells. So it's a new result from 2022. It appeared on Nature. This article is from Nature. And what we can see from that is so how the brain of the fly represents this traveling direction. And what it does, it chooses some a reference that doesn't move. So here it's represented by the sun, and it has the projection into four directions. And then so from the traveling, so here let's say you have this traveling and you have this reference for the sun, so this gives you an angle, and this angle you project it into four directions. Okay, and these four components are literally observed in the brain. So they made the connection with the measures of calcium activity in H delta B cells with these four components, with these four vectors, and from what they measure in the brain, they show that this is the traveling direction. Okay, so you should look more in detail, but that's the idea, and that's uh, incredible. So it shows that the brain of the flies uh, represent their direction with in neurons, and these neurons do some computational vector arithmetic. Okay, so all right, that's it for today. So if you want to get into more details, you have some references on our website for the class. So of course you can have a look at the paper. You can have a look also to start at this website in the Rockefeller University, and you have two videos on YouTube uh, that of the Professor Abbott who talks about his work with his collaborators, and he goes uh, quite in detail. So it's very interesting to hear that. You always learn something from that.